Hi, I'm Alan Ross. I'm the managing editor of APC Media, and I'm delighted to present a webinar today just to moderate this from Ethos Asset Intelligence, which is an MR entrance into the marketplace. For 20 some odd years now, I've been involved in transformers from testing to maintenance, reliability, and as I heard these two gentlemen, Tobias Gruber, who is the general manager, and Alexander Alber, who is a data scientist. As I heard them go through this, it was a delight to see them. So Tobias, welcome. Tell us a little bit about yourself that isn't on the screen.
That's funny. So what isn't on this on the screen would be probably my hobbies, and I like rock climbing.
Rock climbing. Well, okay, so that means you're a
Yeah.
risk taker, but in this, you're not taking any
Yes.
risk. And Dr. Alexander Albert, Dr. Alexander, tell us a little bit about you that is not on the screen. So if we can.
Something that is not on the screen. Okay. So basically, if you see, if I move my head, my camera does track me. So something that is not on the screen is the fact that I programmed this myself.
Okay.
Pretty much
All right.
irrelevant to the topic, but that's what you asked for.
What is interactive art? I don't understand that. We won't go into it because we have a lot to get through. One of the things we're going to do a little bit differently in this webinar is as Tobias and Dr. Alexander go through the presentation, as you put your questions in, I will be able to interrupt them and get the questions answered as they're being asked. If we don't get to all of the questions, which typically is the place that happens, we do have some Q&A time at the end, and we will allow some time for that. And then finally, if we, at the end of this, don't get to all the questions, we will have them answered to you directly through email. But thank you for joining us. And gentlemen, I look forward to this. So Tobias, let me turn it over to you, and if you take control.
Yes, thank you very much, Alan, and welcome to all of you. We are very grateful that you joined this today's webinar, and we have a quite interesting topic that we worked on for quite some time. And I think it's gonna bring you a lot of insights into how our Ethos system works and what's the benefit also in terms of maintenance of power transformers. So first of all, before we start with the new function, with this innovative function, it is useful to understand what an intelligent transformer is, so what we do with Ethos. So typically we have several layers in terms of automation system, and the lower level is called the process level. So on the process level, there are all the typical accessories that you have on power transformers, like the conventional sensors. Every transformer has oil temperature sensors, oil level indicators. Then you might have one or the other intelligent sensor, like a bushing monitor, a DGA sensor, or more innovative sensors for OLTC monitoring, like the vibroacoustic monitoring. There are protection accessories like the pressure relief device or Buchholz relay. And there are also actors like the on-load tap changer or a cooling system. So, and as you know, and as you can imagine, all of these accessories provide data and also can be controlled in some cases. So if you look then on the field level, so on the overall level on the transformer, we call it field level. The first function is to get the data. So to get the data into a single system, to make it understandable, to make it also possible to interpret the data, to aggregate it, and to communicate it. And also, of course, you can see on the upper slide, or on the upper part of the slide, the control topic. So it's also possible to control the actors. And then we have another level, we call it control level. This is typically where the SCADA system is. So it's also important to exchange information between the field level and the control level. Of course, this should be IT secure. It's very important that it is IT secure. This is not today's topic, but you can see it with that little log icon there. And there should be also insights for the asset management. And so this is what we understand about an intelligent transformer, to get all the data that is available on different kinds of transformers, on distribution transformers, on very large power transformers, and get it into a system on the transformer, calculate and interpret the data, and give recommendations and actions to superordinate levels like the control room or the asset management. When we talk about current challenges for power transformers, we see a lot of them actually. I've talked to very many asset managers during the last couple of years, and what you can see is that most utilities are facing higher average ages of transformers, and that means also they are sometimes in unknown health conditions. What does it mean, unknown health conditions? You know it's aged, you know maybe the oil is not too good, but you don't have a good maintenance or replacement strategy. And also more and more utilities tell us that the experienced staff will retire in the next years or has already retired, and less resources for maintenance are available. At the same time, we see a big trend like digitalization and everything that comes with digitalization that we can't dismiss, and everyone has probably wearables like intelligent clocks or intelligent phones, or we talk or communicate now differently with each other. Like Alan is in the US, we are in Germany, you all are around the world. So we have digitalization where we have new business models, where we have new ways to interact together and also interact with the assets. Of course, at the same time, you have to talk about cybersecurity. You don't want anyone that is not allowed to take part of this in that process. You have drivers like continuous cost reduction, that is always a point. And of course, everywhere in the world, we get more and more renewables connected to networks. And this also means that transformers won't be loaded in the same way that they were in the last couple of years. I was at the Bavarian utility just 2 weeks ago, and they showed me a typical power flow of a day on a power transformer that was connected to a photovoltaic station, and you could see jumps of 40 MVA in 5 minutes. So it's not as gradual, and it's not as steady as it used to be. This also means that transformers will age quicker and will need also intelligent devices to tell their status, to tell their health status. And this is where we come more and more into today's topic. Before we dive into it, we talked once again to a lot of asset managers. And when we talk to them, they have typically one sentence that is very important to them. And this is the key thing, is that the asset works. And this is really a sentence that we took deep. So we don't want to implement something on transformers to make it less reliable, but we want to make it more reliable. So we want to make the asset work. We want transformers to work properly. And in order to do this, we have developed a lot of functions, and one of them we will present you today, which really has some key benefits, and hope we can make it clear how it works. But how can we assist asset managers? So what are their parts of their work? So first and foremost, they initiate error analysis and eliminate potential sources of failures. They want to allocate efficiently the resources, so their workforces they have, the money, the services, and of course also they want to assess the risk. So how risky is it to still maintain a transformer which is not too good in terms of health? And these are the 3 focus areas that we touch on today. And I'd like to hand over now to my colleague Alexander, and I'm very grateful that he's also here with me, because he's a big part of the development team of this new function, asset intelligence.
Yeah, thank you, Tobias. So today we are going to take a few excursions to the world of human medicine. And the reason is that the way that Ethos Asset Intelligence works is actually largely motivated by the way human medicine works. So if you go to a medical doctor and you want a diagnosis for what ails you, typically what he or she does is look at more than one symptom. So for example, if there's a child with fever, this could be more than one thing. There's more than one condition that leads to fever. So what the doctor is usually doing is taking tests or looking at more symptoms to make it clear what the actual illness is. Next slide, please. So an example here would be that the doctor could, for example, do a test for C-reactive protein in the blood. And depending on the value, you can be sure that it's, for example, bacteria in a case. So the main idea here, next slide, please, is that if you combine multiple tests and multiple symptoms, you can be more sure of a diagnosis compared to a situation where you only take one indicator and try to make a diagnosis only based on this. Okay, next slide, please. Yeah, this is again a summary of what I just said, but now we are trying to do the same for transformer. So if you think about how human medicine works, as I just explained, we usually try to take into account more than one indicator, and we are trying to do the same with transformers. And with transformers, we can do similar stuff. So for example, we can take into account DGA, cooling, oil. So we have so many different indicators. And usually if something is faulty, more than one of these indicators can be active. And even if only one of them is active, that is still information we can use. So we try to do similar diagnostic strategies to human medicine to get powerful diagnostics for our power transformers.
And to make it a little bit more understandable, so you heard the general concept and we'll come to the implementation of this function later on. I brought some examples to you. The first example is a very basic one, which probably all of you would be able to assume. So let's assume there is a transformer. We got a Buchholz relay warning. So the first warning level has been reached and we get the warning. We at the same time have a DGA sensor installed on this transformer, and we see a lot of H2 generated. So there you would see within asset intelligence a lot of diagnostics, which might be true there, but you see one, so the first one, the shorted winding, the first reason being very probable. So this is what the user of this function would see. And if you click then on shorted winding, you get an explanation of what that means. Of course, in this case, it's very high priority. So you will always see, okay, first of all, what does that mean? Then you will see how critical it is to still maintain the transformer in operation and how to assess this problem. So what the next step for the service, for the asset management is. Yeah, Alan, you have a question.
Yeah, we've got a question. So what is the probability of making, you show really three error codes, right? The Buchholz relay, the higher concentration of H2 or 2 and nothing else. So what is the probability of making the right diagnosis if the customer will use all of the online sensors that MR Group has, as you had in your first slide? So how do you increase the accuracy if you were trying to do that?
Yeah, I think I would skip that question and go to the question later on, because a lot of the things I would need to explain now we see later on the screens. So it would make sense to wait a little bit longer, because then you would understand that how probable it is to diagnose a certain problem. Yeah, but
So for those of us,
we'll keep remembering the question and yeah, and come to it a little bit later. Yeah.
So for those of us who are thinking, how can you do anything with only 2 data points? You're going to answer that for us.
Yes, exactly. And so this is a first example, so to say. Then another example which is quite similar. So we of course have many examples. We also have real case examples from our devices in the field which have some diagnostics already and helped customers to assess their transformer in a very easy way. But let's assume, so we heard the first example, we had very probable shorted winding. But for another example, let's assume we also have a Buchholz relay warning, but in this case we don't have H2, but we have a Duval D1 area, so which means a low energy discharge, and this means sparking. And what you can see here is it has nothing to do with the winding in this case, but it is due to a contact error in the selector. So it's a problem with the OLTC. So, and also for this case, you can see it's very probable. You can see the bar is almost completely full, and we always then explain, okay, why do we come to this conclusion? First of all, we see that the low energy discharges, we see that the Buchholz relay warning level reached. We also see some evidence against it. And then we again describe what does this error mean, how critical it is. In this case, it's medium priority. It's you can still maintain the transformer in operation, but it's useful to make a DGA of the so to have an offline DGA in the laboratory, also to make a vibroacoustic measurement on the selector in order to be sure what happened there, and you probably need to have maintenance on the selector of the OLTC. So 2 examples, 2 similar events that we saw, but 2 completely different diagnostics. And also you need different people to assess the transformer. The people who can assess windings are not necessarily the people who can assess the OLTC. And so you directly have an indication of what the next step is. You can directly go to your service staff and inform them what the next possible step is. And so what we did in the past and still are, and you are probably, if you talk about transformer monitoring, you will know that there are a lot of event lists. And we talked to asset manager, and they always keep telling us, I have hundreds of transformers. If I only have 2 events for each transformer, I can't assess it. It's not a help in my work. I want to be able to assess it. I want so it should give me a benefit of putting monitoring on my transformers. It shouldn't cost me more time because of a faulty sensor or something else, where I only have problems and I only have additional work, but no benefit of it. So you see here another example. So you see a lot of events in this case, that some voltages are not available. There is a motor protective switch triggered. We have some invalid temperatures and other things. But the question the asset manager asks themselves are, what should I do next with the transformer? So is it risky to keep it in operation, or do I need to send someone to the transformer in order to make a maintenance? And so this is what we did there. We interpreted the events, and it's I always have this image in my mind where there is a little expert looking into the data. having access to all data that is available to the system and giving a recommendation. So a little asset manager, a little expert, a little consultant looking at the data that has been recorded, looking at the events that have been present, and giving qualified failure diagnosis. We did this, and we developed this together with many transformer experts we have here within MR, but also external resources from literature. So we have the most common, let's say 40 to 50 transformer failures. We know how often transformer fail because of these. We also have sensors, so we know how reliable they are, and this is all part of this function and has been all taken into account when we have developed this function. And most important is not only show that there is an event, but give concrete recommendation to have the correct measures, so the correct next steps. We do this, and you might be familiar with this slide. It was also presented in the IEEE. We can actually reduce transformer failure rates by using monitoring. So first of all, what they did, they compared transformers, and then they added routine offline inspections and also existing means like every transformer has nowadays, like the Buchholz relay, like the routine all measurements. You can reduce the absolute failure rate of the transformers by about 30%. If you have monitoring installed and additionally measure all the different parts of the transformer, you can reduce the failure rate by another 42%. And then, of course, you need to know what you are capturing there. You need to interpret it. It's not the data that is showing the information. You need the information, but the goal is to go even lower with the failure rate. And there is the potential due to using machine learning and other functions that we will talk now. And why do we do this? Our overall goal is to show failures before they occur, reduce the repair costs, improve reliability, help the asset manager to better use their capital and less workforce, and also have less unpredicted downtime. So this is our overall goal for this function that we always had in mind, and it should provide benefits and not cause more work. So this is why we have implemented asset intelligence. And now let's come to how asset intelligence works. Yeah, Alan, you have a question.
Yeah, we have a number of questions, and I think they're going to be answered next, but I don't want to lose the cadence here. What algorithms are created for each parameter being monitored and then analyzed, and are you using machine learning to do it? Because there was a concern about the original examples that you gave, saying it doesn't appear that both examples had sufficient data to conclude or locate the fault in the transformer. My assumption is that's true if you don't have something like ETOS. So I think you're going to go into that next. Thank you for the question.
Yeah, we come into yeah, exactly. We come into how asset intelligence works just now, and for the examples, we made sure they are very, very basic examples, and of course you can't locate the error as well as shown there. It's only a very basic example to make clear that even only the presence of one event or another event can make a complete different diagnostics, and this is why it's so useful to have a tool like this to take into account all the possibility of the data that is captured. But how this works, Alexander will come to that now.
Yeah, I think I can also talk a bit about those questions. So the first one, it's not actually machine learning what we do. The system is mostly based on expert knowledge. There is some data used to train it, especially for the failure base rates. but most of it is built based on expert knowledge. So I wouldn't really call it machine learning. And about the other questions, I'm not an expert on both of these examples, but based on my experience, if you have lots of discharge gases in your transformer, in most cases, this is actually the fault of the OLTC. It doesn't mean that there's a fault, but usually it's related to at least some OLTC leakage. So I'm not an expert for the first case, but for the second, this seems fine to me. So if you have any further remarks, maybe we can get in touch. But to me, it looks correct based on what I know about DGA at least. Okay, anyway, how does asset intelligence work? The thing is that we want to combine multiple systems and models that we already have. So when we look at a typical transformer, we have monitoring systems, and sometimes there are also small models connected to these monitoring systems. So what could a model mean, for instance? If you have both an ambient temperature sensor and a top oil sensor, and you measure the transformer load, you can use this to compute the terminal resistance of the transformer. And this is a value that should stay roughly constant as long as the cooling doesn't change. And this is something we already do on ATOS. And lots of models like this can be used to further to give meaningful values that can be better for diagnostics than just the original sensor values. So we use models like this. But we also use statistical data, for example, from the SICRE Transformer Reliability Survey. And what we also use is our own knowledge about the reliability of these sensors. I will talk about this especially in the next slide. But in the end, we use a thing called a Bayesian network. So it's not a neural network, it's a Bayesian network. That's something different. To integrate all the stuff and compute fault probabilities. Okay, next slide, please. I will again do another excursion in the field of human medicine, just because it's so useful to explain this. In the last years, we all became at least somewhat experts on how these cheap, rapid at-home COVID-19 tests work. So you might already know that they are not perfect, but they have a thing called sensitivity and they have a thing called specificity. So what does this mean? Let's say that if you have a COVID infection, a cheap test can detect it with a probability of around 60 to 80%. So it won't detect every infection, but it will detect most of them. And this probability is called the sensitivity. And as you might imagine, we can define something similar for our transformer monitoring systems. And there's also a thing called specificity, which is related to the negative information. So let's say we don't have COVID and we do a quick test, or let's say we do a test and there is a detection. Does this mean that we are infected? Not really, because there could be a false alarm. And this is where the specificity comes into effect. So for these cheap tests, there's usually, depending on the manufacturer, between a 90 and 97% chance of being infected if you have a positive result. And this number is called a specificity. And again, we can define something similar for our transformer monitoring systems. Okay, next slide, please. So how do Bayesian networks work and how can we use them to include knowledge like specificity and sensitivity? Basically, Bayesian networks are graphical probabilistic models. So here we look at cause and effect, and we basically draw arrows from cause to effect. So in our case, the causes would be the failures or faults on a transformer, and the effects would be monitoring systems reacting to these faults. And of course, there can be intermediate steps. So a graph like this can get quite complicated. But the interesting thing is that networks like this can be manually developed. So you would have to look at questions like if the bushing has failed, how large is the probability of a bushing monitoring system detecting this? And here is where all these numbers like sensitivity and specificity come into effect. And this is actually a lot of work, but this is actually also doable by experts, even if it takes a lot of time. And with a system like this, you can basically define a complete Bayesian network for your power transformer. And you have a question?
Yes, and it's a good question because it's a number of people have asked in this vein. So what are the minimum inputs needed to have the ETO system working as expected? I mean, and what is the hierarchy of those inputs? If you could only do one thing, what would it be to make ETOS work? If you could do several, because you see them up here, you've got a lot of monitoring systems that are either working or attached to the transformer. What is the minimum to make ETOS work in your Bayesian network?
Yeah, this is actually the perfect slide for this, because on the right side, you can see how we can use our finished Bayesian network to do inference in the field. So the nice thing is that a Bayesian network can be used independently of the number of systems you have installed. So this is a bit of a flexible system. If you have no monitoring systems at all, then of course,
Alex, we're having a very hard time hearing you. Tobias, can you kind of help on this one?
Okay. Yeah, sorry. I also couldn't hear you, Alex. I think your microphone might be, there might be a problem with your microphone. But we'll have actually a slide on this. As Alexander said, it's a modular approach. So that doesn't mean you always need the full range of sensors and data, but you can make diagnostics more reliable and more accurate the more information you have. So it's pretty hard to give an exact answer unless we have a set of sensors that are connected direct already on the transformer. Then we can calculate it because we have this big Bayesian network. But we have a slide later on showing the impact of the single sensors, and there are some which give a lot of information and help a lot on reliable diagnostics of the transformer. But we'll come to it in 2 or 3
small
slides.
mic check. Is it better now?
Yes, it's better. Yeah.
Okay. So I hope it was just a small and short internet interruption. But a Bayesian network is basically flexible in the sense that you can choose to set those nodes where you have actual measured information. And if you don't have information, you just leave it like it is. So this is basically the right side of the slide. Let's say you have out of these 6 monitoring systems, this is not actually Ethos AI. This is just an example network that looks similar. But here we have 6 monitoring systems that could be installed. If you have only 3 of them, then those values can be measured and set fixed. And you can then compute backwards to updated fault probabilities. So this is flexible in the sense that it just uses the information you have. And of course, that also results in a bit of a garbage in, garbage out system. So if you don't have any information, then it will just the output the base probabilities, which is not useful. But for each given set of monitoring systems, it gives you the best guess of what this could mean for your fault probabilities. So there is no minimum required amount of monitoring systems, but some are more useful than others. And there will be a slide later where Tobias will present the systems that are most useful for the system. Okay. Next slide, please. Okay, so I roughly explained how this works technically, and this is a slide about why we are doing it like this. So what are the advantages of using Bayesian networks for this? As I already said, we are not doing machine learning, but machine learning is not equal to artificial intelligence. So it's basically a subset, but you can do artificial intelligence without doing machine learning. And this is especially useful here if you have not enough training data. And since transformers are big, expensive assets, they don't actually fail that often. So we don't have historical information about thousands of faulty transformers together with postmortems and together with all the monitoring state. So this would be difficult to do with machine learning actually, but it can be done based on expert knowledge. And another advantage is the thing we already talked about. So this stuff works even if you don't have every possible monitoring system that the system can handle, because usually you don't, usually you only have a few. And another nice feature is that Bayesian networks are transparent. So it's not a black box model. You can basically understand what's happening. And if there is a strange diagnosis, you can look into this and see why the Bayesian networks thinks like this, and this makes it easy to explain it and to debug it.
Before we
and
go too
now
much
back to
further,
Tobias.
yeah, before we go too much farther, we love acronyms, don't we? And we've got a question that I also have. What is an HX failure? What does that mean? And LOOC, what are you referring to there? That was on a previous slide.
Okay. I think HX is heat exchanger and LOOC is loss of oil. I'm not sure. It's only an example. Loss of oil cooling.
Loss of oil condition. We can go on from that, but there was a question.
I think it just means that it's not tight and the oil is running out of the transformer. But I forgot the actual acronym.
Maybe once again to make it clear, it's only an example here. Okay. None of the numbers that you see there are correct. None of the failures that you see here are correct. It's only there to show you the mechanism of asset intelligence.
Yes, our actual Bayesian network is a lot larger, and also we don't want to show it here for obvious reasons, and it would be too big to be useful for explaining it.
Okay, and what countries did the data, are you primarily in Europe or have you done this in different countries? Because there are different parameters.
There are actually, yes, and we equip a lot of transformers already with Ethos Asset Intelligence because it's always part of Ethos. And of course, the more sensors that are connected to Ethos, the more data we get. But we have already supplied thousands of Ethos systems all over the world. Yeah.
Okay.
What types of errors? Now we come a little bit more into the direction of the question earlier on. What types of errors can be detected? Of course, when we talk about transformers, we have different components of transformers, and we have, for example, the core. If the core is not grounded, there will be things where or how you could detect this. These are always examples of possible errors that we could detect there. Of course, there are more, but just to show you an example, we can have problems with the tank. There can be leakage, there can be air intake, for example. We can have problems with the cooling system, that the fan is blocked, so there's a fan error. We can have problems with the bushings. For example, there's a partial breakdown of the capacitive layers. We can have problems with the windings, like you saw earlier on. We can have problems with the onload tap changer, and of course also with the paper insulation. So all these components will be part of asset intelligence, and of course it's useful to have the sensors measuring data giving data to asset intelligence for it to be capable of giving diagnostics. And now we come to the slide of which kinds of sensors are relevant for the function. So I'll come back to one of the first slides that I've shown. Of course, it's important to have temperature and oil level and to include the intelligent sensors, the protective devices, and the actors, and all generate data and all help to get more accurate diagnostics. But if you only had 3 sensors or 3 data generators on transformers, what would they be? We would recommend to always have DGA, bushing monitoring, and a Buchholz relay. Ideally, a Buchholz relay where you have also a warning level, and those 3 can really help in providing very accurate diagnostics within the Bayesian network. So of course, everything will be connected and other systems will also help making diagnostics more reliable. But if you only had 3, those were the 3 with the biggest impact. And again, I don't think there is another system which takes into account also the accuracy and of the sensor, for example, because when I talk to customers, they had problems, for example, with the bushing monitor, they had false alarms. But as Alexander said, we know the probabilities of that happening, and so we can take this also into account, and it will show up if this is a false alarm and the data show it's not probable that the bushing has failed. So this is why it's useful to have the system enabled. It's useful to look on the evaluation of this system in order to get very accurate diagnostics and in order to know what the next step is in order to assess the transformer, to maintain the transformer, and therefore, in order to conclude, so we have shown you today asset intelligence. It's a Bayesian network system which we have developed together with our transformer experts. We integrate all data from multiple monitoring systems, from multiple sensors, and it's as intelligent as the number of data sources are connected. And there, with this system, we help the power system operators, the maintenance engineers, and of course also the asset manager to detect the transformer failures, to have some kind of a consultant directly enabled in ETOS. And this provides a significant advantage, like you saw it in the past, like you had monitoring system in the past, because it's much faster, it's much more reliable, and it only helps to be more risk assess, to be more risk aware and to know how your fleet is doing at this exact right moment. So thank you all for listening, and we can go a little bit further into the discussion now.
So we have several really good questions. The first one is, you talk about all of the data that you've gathered into the Bayesian network. How many data points, or just give us the scope of data points that went into ETOS and the scope of the experts that you brought involved into it?
So in terms of the data points, I would say, Alexander, please correct me if I'm wrong, but up to 50 something.
It's a number between 20 and 30 data points, and data point meaning here, is there an monitoring system installed, and if yes, if there is some event happening. So a data point is more than a yes or no. It could also be a negative result. So for some number between 20 and 30 different monitoring systems or sub monitoring systems, we use the information if the system is already installed, and if yes, if there is an event or not. So also the negative information is used.
How many events? So if you take this also into account, for example, for bushing monitoring, we have capacitors, we measure capacitance, we measure or we calculate the dissipation factor. We have other things that we look on. So if you take that into account, it must be way more than 30, right?
No, it's between 20 and 30, okay, taking this into account.
Yeah.
Okay. Let's looking at it different. Do you take third-party sensor data in at the same? Also, people already have monitors.
Yeah, sure. Absolutely. So Ethos is a completely open and modular system. With open, we don't mean it's open to hack it, because cybersecurity is very important to us. But here it was on purpose to not show any brand names, because as we know, customers like different brands, like to have different sensors, and it works with all sensors. Of course, if you have better information about the reliability of those sensors, we expect our sensors to have a certain reliability that we have programmed in the Bayesian network. If this is different to the sensor that is connected, it might change a little bit in the probabilities of the diagnostics, but I'm pretty sure that most sensors work pretty well on transformers, and we can use the exact same numbers also on third-party sensors. Yes, of course. So the answer is a clear yes.
Is there a self-learning function to this from our, not just for one transformer, but for the entire audience of transformers that goes into Ethos? Are you constantly using AI to learn more and get more accuracy into it?
It's not self-learning. Also, there would have to be lots of fault cases together with post-mortem information to actually be able to do this as a self-learning model, which is why we didn't use machine learning anyway. So it is possible to train also Bayesian networks based on data, but we didn't do this because there's just not enough data available, and it would take millions of thousands of transformer years together with the corresponding monitoring system state to train a system like this. So it's at least in the current year much more feasible to build this only based on fault statistics and expert estimations.
So when you're talking about the AI part of this, are the IEEE, IEC, the global standards that they're providing, is that what you're using to determine cause and effect?
It's one part of it, as Alexander showed. So having the fault-based rate and looking into the literature, of course, helps. So that means if we have a really rare case of a transformer failure, it is not as probable. So if the data of the sensors would show that it is this fault, it's not as probable. And we take also other things into account because of this. So this is useful information for sure, but it's not the only information. Of course, also the sensors themselves, the models, and the reliability of the sensors are also a big part of the function.
So Ethos,
to add to this, some models are actually used before the data is input into the Bayesian network. For example, for DGA, if you have enough gases measured, then the Duval triangle is used to do a fault classification, and this is then input into the Bayesian network. So for some aspects, we use models from literature, for example, the mentioned IEC literature, before we actually enter information in the Bayesian network. So stuff like this is used at least as part of the model, but the Bayesian network itself is mostly defined manually by us. So that was a custom model.
So consider someone who has a multi-gas monitor, a DGA monitor, and it gives direct information using Duval's triangle or pentagram. what is the value of then, if that's really your primary function, what is the value of Ethos to take that and bring it into the Bayesian network and give a more accurate, response?
Yeah. So, like Alexander said, you then, if you give it into Ethos, you probably then not only have the DGA information, but also temperature or other parts of the transformers that are connected to the asset intelligence Bayesian network. And so that means you can make it more clear in terms of the diagnostics. But even if you had only the DGA values, you could enter this, and you would also have an idea about how probable it is, so how a typical failure would be in terms of looking at the fault-based rate and sensor reliability. And then you would also get a list like I showed previously, like this one, with several causes that may be true and how probable they are. But you would get the exact same interface. You would get the diagnostics based on the DGA, and then that can be detected by DGA.
By the way, you're showing your whole slide deck. You referenced one single slide. You might want to move to that slide, but we go to another one.
Oh, really? I thought I was sharing my presentation.
You're showing your whole slide deck. So
I can see slide 22.
Yeah.
Okay.
It should show slide 22. Yeah.
There you go. Okay. Now we can see.
To add to the previous points, Duval only gives you a fault classification, but to do this, you have to be sure that some fault has actually occurred. So in reality, if you just look at DGA, you also have to combine some fault classification method like Duval with some other method like the thing, I think it's C57.104 that you can use to determine if some fault has actually occurred. So even with DGA, you already have to combine several methods to be sure that what you're doing is legit. And the Ethos S Intelligence basically does this work for you and also includes non-DGA data points. So that would be my answer to this question.
Yeah, and also, I mean, you could argue if you talk about intelligent sensors, how important it is it to have a really powerful CPU on the sensor. So it should be reliable. It should give out the raw values. It should provide really accurate information. But should it really calculate, for example, directly the Duval or other things on the sensor itself? So what's the benefit of it? So if you had a very capable CPU near the transformer that could perform every model, that could calculate every model, that could help having a global view on the transformer and a holistic view on the transformer, and not only look at one single set of values like the gases, but also the temperatures, the capacities, the I don't know what, the tap change operations. Yeah.
Okay. Does Ethos take into account load?
Yes.
Okay. You mentioned it and kind of bypassed it. One of the biggest concerns right now is cybersecurity, and how does Ethos avoid being hacked with bad data that causes it causes Ethos to fail because of hacking, because you are allowing other data to come in. So how do you prevent that?
Yeah, so it's a topic by itself, and maybe we do a webinar on cybersecurity as well. I think it might be quite interesting for people. But typically, Ethos. So of course, external audits are very important. So you let external people try and hack your system. This is done by utilities. This is done by consultants, and they help us to proof that our system really is secure. What does secure mean? Of course, data needs to be very stored on the device without someone getting into the device. So it's very important to have encrypted communication. It's very important to have user authentication. That means only the people that are in charge of using the data can see the data. And there are different mechanisms that are important there. But to go in detail, I think it's a little bit too far for this webinar. It's only if there's really interest, we can do a webinar on it, I think, because there's more to it in terms also of certification, in terms of how do you provide ethos or other systems with software updates in case there was an incident. Because I mean, we know it also from our phones, incidents happen, but the response from the suppliers, the response of the manufacturers is very important, and there need to be processes in place to inform the utilities in order to know how. It's the same with the transformers, how risky it is to still operate the system, and how I can quickly have a firmware update, and what the next steps are. So
Tobias, last question, because I agree with you. You need a whole series on cybersecurity, data integrity on that. But last question, can you give an example of actual when you installed ethos on a system, and just a use case? You don't have to mention the customer, but give an example, or maybe we only have time for one, but of how ethos was able to be used to detect a problem that was then acted upon by the utility or the owner.
Yeah, we have actually a real case scenario which we haven't included in this slide, but we can provide later on. We had problems on a pretty new transformers, and one of our DGA sensors showed high concentrations of H2, and not only the so the absolute limit value wasn't reached yet, but we could see that the rate of change was increasing very quickly. And so Asset Intelligence had diagnostics. I can't remember exactly what the diagnostics was, but the transformer operator was very skeptical at first. But then they asked us what is wrong with our system, and we said, yeah, we assume it works in a correct way. They performed the oil measurement, and the laboratory said, okay, it is true what the sensor is saying, it is true, so we should take the next steps. And so what we did with Asset Intelligence was informing the customers that there is a probable fault of the transformer. There is something to be checked. The laboratory confirmed, and now the next steps are taken. But so we can set this example later on to the viewers. I think it might be quite interesting.
That would be good.
Yeah.
We have some other questions, but we don't really have the time to get into them, so they will be given to you all at a different time. But Tobias Gruber, thank you so much for working on this and developing it and presenting today. Alexander Alber, thank you, Dr. Alexander. We appreciate both of you very much.
Yeah, thanks.
Thank you very much.